All right, so apparently this didn't stream out last time, and I've actually got it in the background now to make sure it's streaming out. So I need to go through all the questions I was answering Tuesday, as well as the questions I received Wednesday. Yesterday was a federal holiday, so there was no live stream, didn't do anything, and that leaves us with today. So I got the chat menu up. If you type anything in the chat, full disclosure, you're probably looking at another 30 minutes before I get to it, unless it's a really quick question. All right, so all these questions are around organic. First one is question 5 on the homework. How many alkenes have the molecular formula C5H10? Now, back from the alkane material, saturated alkane, branched, saturated, C5 is going to be H12, so we only have one double bond, and we don't have any rings because we're not missing enough hydrogen to generate a ring. Easiest one to do, start with pentane, 1, 2, 3, 4, 5, and then you've got the terminal, and then you've got an internal alkene. Now, if we put the double bond here, we're going to basically have the same thing, just rotate 100 degrees. The trick with alkenes, though, is remember that you have cis and trans conformations. So with this one, you're going to have both the cis and the trans forms. Now we can start moving methyl groups. So we take this methyl group, move it over here. Oops. We have the this is 1-butene with the methyl group moved, so that's the 3-methyl-1-butene. We can also move the double bond over, and this will give us the 3-methyl-2-butene. And we can also put this methyl group here on this carbon. There are no cis strands for this one or for this one because, well, for terminal alkenes, there's no cis strands because it's a terminal alkene. And for this one, if you look at the symmetry, it ends up not making a difference. So actually, if we look at, oh yeah, so this is correct. So we have 1, 2, 3, 4, 5, 6 possible alkenes. If I remember correctly from Tuesday. Yep, that's the correct answer. So there's 6 alkenes. Again, my approach, draw the linear, do the terminal, start working your way through the internals. With any internals, do the cis strands, and then start moving your methyl groups around. Right, next question was question 6. Give the IUPAC name for this compound. So we got our double bond, CH3 group, 2 alpha groups. So that's that 2 CH3 CH2. Longest chain, 1, 2, 3, 4, 5. So this is going to be a pen T. We want to minimize the number of the double bonds, so it's 1, 2, 3, 4, 5. So 2 pentene, and then 3 ethyl 2 pentene. Now the reason we don't need the cis trans here, we have 2 groups that are the same, so there's really no point using it. So if I use the 3 ethyl 2 pentene, that ends up being correct. All right, next question is question 8. Which is the more stable? 1-methylcyclohexene, 3-methylcyclohexene. So they're both cyclohexenes, but one is 1-methyl, the other is 3-methyl. Big thing with, alkenes, the more substituted the alkene, meaning the more carbons we put around it, the more stable it is. So this is going to be more substitute because this is a tri-substituted alkene, so 1, 2, 3. Versus this just being a di-substituted. This is not something predicted by Lewis theory. This is something that comes about from empirical. You have to go to molecular orbital theory in order to prove why this is more stable. But what we would call this, what we'd say is that it's the 1-methylcyclohexene, and the 1-methylcyclohexene contains a tri-substituted double bond. Next question is question 11. So you want to place a double bond, you want to make this the Z3-methylcyclododecene, and they're nice enough to kind of give you the starting compound. All right, so the thing is that if this is the third position, so we know it's a 3-methylcyclododecane, we have to count two carbons out to figure out where the double bond could be. So 2, we could have a double bond here, or we could have a double bond here. So the question is, which of them would make them E or Z? Well, the thing is that on both of these, we have hydrogen, which will end up taking the lowest priority on both sides. So really what we're saying here is that Z equals cis and E equals trans. Now the thing is, this is not always true. This is only true if the two of the groups on opposite sides are hydrogen. Because what will end up happening is the lowest priority groups will end up being on the lowest priority groups will always end up being hydrogen, and whatever's opposite of them is always going to be higher. So we can use the cis-trans synonymously in this case because the priority rules for CIP, Coning-Gold-Prelog, also match up with the rules for cis-trans where two groups have the same priority. In this case, they have to be the lowest priority. So what we're looking for is a situation where we end up with a cis. So if we go with the double bond here, we're going to end up having the hydrogens trans, so this doesn't work. If we put the double bond here, this ends up having the hydrogen cis, and this gives us the Z conformation. So the solution here is to take the structure they've given you and put a double bond there. Now, again, I want to emphasize that cis does not always mean Z, trans does not always mean E. It's because we have two hydrogens around these double bonds that we're able to make this equivalency of Z and E. Now, the next question is 12. I'm going to pull this question. I'll talk about how the solution works for it, but I don't like this question. And the reason I don't like this question is that it's conflating what could happen with what does happen. So to ask how many alkenes would you expect to be formed from the following alkyl bromide under conditions of E2 elimination? That is a fair question. And the reason we're having to make this E2 distinction here is that we're not going to have a carbocation. So what it's asking is what do you expect, but it's not actually asking you what's the majority product, it's asking you what could happen. And in order to get this E2 elimination, I can see what they were trying to do with this question. There is stereochemistry associated with E2 in that you have to have the bromine and a hydrogen antiperiplanar, meaning that the bromine has to be able to rotate in such a way that there's a hydrogen opposite to it across the bond. The thing is that this is a linear alkane. It has conformational rotation, which means that all this thing has to do is rotate around this double bond to the point that it will undergo elimination. And because we have these two methyl groups when we finish, there is going to be no symmetry associated with it. So you could argue if you do E2 elimination, you get both this and this. The problem is that if you just take this and rotate it 100 degrees in plane, you get this. So there's nothing associated with the E2 here that would somehow make this give you a different product if you did it by E1. Because the other thing about E1 is that the bromine is going to pop off and give you a carbocation, but the carbocation is on a tertiary carbon. It's not going to move. So the E2 really doesn't have any implications. You're going to form this 2-methyl 2-pentene. But what I don't like about this problem is that they're also saying that you can get elimination from here as well. And I had to look up the answer when I was working on it, apparently by myself last Tuesday, was that there's two answers here. This one and this one. And the reason I don't like this is that this is Zaitsev's rule. This would be an anti-Zaitsev formation or conformation. I'm sorry, product. And what doesn't make sense to say is like, well, what could happen? Like, well, technically anything could happen, right? So, I mean, who's to say that you don't do something else? And my problem with this is that this is all we expect to see by Zaitsev's rule. This in principle could happen by E2, but it's very much the minority product, but this problem acts like it's the majority product, or it's insufficient quantities. So the answer here is 2. And it's these two compounds here, but again, I disagree with this problem because I don't think you should be counting this product down here. So it's going to get eliminated when I get a chance to actually sit down and like go through the homeworks. All right, question 13. Identify the alkene obtained by the dehydration of 3-ethyl-3-pentanol. So when we do this elimination, you look, this is kind of symmetric. It's really got 3 ethyl groups around the OH group, so there's your pentene. It doesn't matter which way we pull the double bond. These are all related by rotation, so we can just look at it this way. So what we're going to end up here, our parent chain is a pentene. So it's 2 pentene with a 3 ethyl. So we have, ooh, did that terribly. So we have 3 ethyl, 2 pentene. So that's it for that first email. Second one was asked about alkenes and syn reaction, specifically hydrogenation, and when hydrogens are added, it doesn't matter if they're added at front or back. I noticed an example that the hydrogen at the front, so is there a preference for which one takes over? So all alkenes here are trigonal planar, specifically the carbons that are involved in them. So there is a top and a bottom, but the top and bottom are related by rotational symmetry, which means that if we draw a line through this double bond, we can rotate it 180 degrees and never tell the difference. I mean, you could say, well, I can see it, but in terms of the bond symmetry, it doesn't see it. And because of that, there's no preference for top or bottom. So whenever we have a reaction with alkenes, we get addition to both what we would consider the top and bottom. So let's say we had an asymmetric alkene. And we were to hydrogenate. Well, the thing is that we're going to get hydrogenation to the same side. We're going to end up getting one where the hydrogens are added to what we would consider the top. And then we'd have one where the hydrogens were added to the bottom. So the big thing with the syn addition and anti-addition is the relative placement. So with the syn addition, the hydrogens are added to the same side, and for bromination reactions or halogenation reactions, the halogens are added on opposite sides. What this means is that with alkenes, we do not have stereospecificity. We end up with a mixture of both the R and the S's when we're done. And this is the problem with taking alkenes and trying to give them chirality, is that generally you may end up with a racemic mixture of both because there's no preference for top or bottom. They're both thermodynamically equally likely to occur. So let's say for whatever reason this is the R and the S conformation here, we would end up with the S and the R on top, and these would be in equal amounts. Now, this does have implications about the diastereomers. So we'll always end up with enantiomers. We'll end up with both equal amounts of the RS and the SR, but we won't end up with a mixture of SS and RR. So we're always going to get enantiomers, but what specific enantiomers we'll get, those R and S centers, will depend on whether it's a syn or anti-addition. Now, the way I was taught to remember syn is that syn is same side. So S, S, S. So syn additions are to the same side of the double bond, meaning that when the two things get added, they get added to the same side. For an anti, they're on opposite sides. This comes from your Newman projections, where if we're going to add a group, they get added anti in the Newman projection. So there's your anti. But again, you're going to end up with both. So let's say this conformation here is R and the back side is R. You're also going to end up with an equal amount of the S and the S. But the thing is, you won't end up with a mixture of RS and SR. It's only RR and SS. And if you had the same side, it's going to be the same thing. So we end up with an equal mixture of the enantiomers, but we don't get any of the diastereomers. All right, next question. metathesis on page 12, the bromine light mechanism, the Diels-Alder mechanism on page 13, the potassium permanganate mechanism on page 14. So let me download. Now, I'm going to answer a question later in this live stream, and it was asked about mechanisms. I do not see merit in memorizing mechanisms, particularly for things above your SN mechanisms, your E mechanisms, and Markovnikov. The big reason, and I'll get to it, is that the mechanisms here are at best approximations and are at worst wrong. Page 12. Okay, so the metathesis mechanism is not important to know. And the reason why you don't need to know the metathesis mechanism is that Schrock is the ruthenium one. By the way, I did a lot of thesis work on metathesis catalyst. So the thing is that anything involving a D metal or a transition metal cannot be described by Lewis theory. Well, this kind of creates a problem because we're using Lewis theory in organic chemistry. So what's going to be the problem? Well, Lewis theory doesn't have d orbitals in it. If you look at the original formulation for Lewis theory, there's no d orbitals. And that's what's doing all the chemistry with ruthenium. So what happens with ruthenium and your alkenes is that you get what looks like electron donation into what's called the antibonding orbitals of the double bond. And this breaks the double bond and ends up generating a bond between the ruthenium and the carbon. So we get kind of this cyclopropane intermediate. So the ruthenium binds to ethylene and the ethylene binds back. And then on the other side, we get the same effect. That our double bond here binds to the ruthenium and it ends up forming the cyclopentene intermediate. Now, what will happen is that this is a reversible reaction. And so what will happen is that this bond will break and these two carbons, or these four carbons, will form bonds with each other. So they're going back and forth, or making and breaking these bonds. But again, none of this is predicted by Lewis theory. You don't have antibonding orbitals, you don't have d orbitals, and you can't explain d orbital chemistry. So in my view, memorizing the mechanism for the Schrock catalyst, the Grubbs catalyst, the ruthenium oxide, the tungsten oxide, they all go through what's called a pseudo-Wittig intermediate. If you take organic 2, we'll talk about the Wittig reaction. It's a lot of theory that doesn't do you any good to know. So practically, how do you work with a metathesis catalyst? Well, what you do is you draw a line through the double bond, and you define the fragments. So we'll call this A, B, C, and D. So A here is a methyl and a hydrogen. B here is an ethyl and a methyl. And I'm just going to draw a line here because that's how we broke it. And C and D equal the same thing, and they're this two hydrogen group. So now you build your Punnett square. So we stick A to C and we get propylene. We stick B to C and we get this compound. And it's going to look the same for D. So we'll end up with 4 terminal alkenes, 2 with methyl groups, and 2 with this methyl ethyl group. That's all you really need to know about how to predict a I'm sorry, there's a bromine, not a methyl group. Bromine. And that's kind of it. That's the big picture of metathesis, is that you end up getting this mixture of A, B, C, and D. It can get super complicated super fast. And the reason why I say in large excess is that pretty much we're also going to have this and this floating around, because these can turn around and do metathesis with themselves. So we can take this compound and split these two, and this fragment will react with this fragment. So with metathesis catalyst, unless you're running a large excess of one, you're going to end up with a mixture of every possible combination. So by doing the ethylene in large excess, we pretty much only end up with the products of this compound reacting with this compound. Ideally, what you would work with are very simple fragments, and that's pretty much all that you're going to see dealt with in terms of exam material and discussion board material. Very simple examples. But you can get to all of this without needing to know how the Schrock or Grubb catalyst works. So again, take your two alkenes, split them down the middle, define your fragments. You should have 4, A, B, C, D. In this case, C and D are the same thing. Build a Punnett square, and that's what you're going to produce. The challenge with these is if these metathesis products react with themselves. So if this does metathesis with this, if this does metathesis with this, if this does metathesis with this. The next question, Diels-Alder on page 13. So Diels-Alder is another one. This is not predicted by Lewis theory. And a criticism of Francis Carey, the book we use, it is a legitimate criticism, is that it is a very theory-heavy book. It is written by professors for graduate students. Now, it's weird because it is like the golden standard for undergraduate textbooks, but it's odd because the book really is too high level for an undergraduate book, but a lot of the other books aren't nearly that good. So what ends up happening with, and we'll start with just very simple Diels-Alder, is that we've got, if we look at these pi bonds, we've actually got these bonds above and below. So if I draw them kind of like at an angle, we've got a p orbital sticking above and below to make these double bonds. What they can do is they can bond with each other. And this is how we end up with a cyclohexene product, is that these two p orbitals split, these two and these two p orbitals split, and the p orbitals end up overlapping on this side to create a sigma bond. And these two come together to form a pi bond. Now again, Lewis theory doesn't predict any of this. It doesn't predict bonding and antibonding orbitals is what you need to make Diels-Alder work. So, how do you practically work with a Diels-Alder reaction? Well, you don't need to know the theory. What you need to know is the pattern. So the way I teach Diels-Alder is that you need to draw your diene, and you need to draw your diene. Well, we'll start with just this. Now, the symptom of all Diels-Alder reactions, particularly with just alkenes, we'll talk about alkynes in the next chapter, is that you always produce cyclohexene. So when this gets done, there should be a cyclohexene ring in the molecule. Now, how do we keep track of what's what? Well, number 1, 2, 3, 4. In this one, we're going to do alpha and beta. You can do A and B, whatever works best for you. In the final product, this is where the carbons are, 1, 2, 3, 4. And alpha and beta always appear opposite that double bond. So alpha and beta here are always going to be opposite the double bond. Now to figure out what the product is, just look at what's bound to each of these carbons. So 1 had 2 hydrogens bound to it, those 2 hydrogens are here. 2 had an ethyl group, so that's where that comes from. 3 had a methyl group, so that's where that comes from. And alpha also had a methyl group. Now, Diels-Alder is a nightmare-like metathesis because I arbitrarily drew them this way. So I can have a methyl group up, I can have a methyl group down if I just start with this molecule flipped over. I can draw the methyl group up and the ethyl group down and get this. Now, the only rule here is that if these two are cis, the hydrogen and, well, honestly, cis doesn't make sense in this case because we got 3 groups that are the same. But let's say we had 2 methyl groups. Both methyl groups would be cis relatively to each other, and because this could attach either way, we'd have 2 wedges or 2 dashes. So you end up with basically 4 possibilities when you're done. One where the R is drawn. So I'll show you the Punnett square down here. One where we draw the alkene like this, or the dienophile like this. One where we draw the dienophile like this. Run out of board space. One where we draw our diene with the ethyl group up, one where we draw our ethyl group down. And we will have all 4 combinations, every single one, with a cyclohexene group. And honestly, with these, we don't even really bother with the stereochemistry. We always get the relative configurations. And so you'll end up with all 4 possibilities. This is where a Punnett square is going to come in really handy. The other one was question potassium permanganate mechanism, page 14. So potassium permanganate is another one that it's a transition metal. And so to describe what goes on with potassium permanganate, to try to apply Lewis theory to this doesn't work because Lewis theory does not describe d orbital chemistry, which is what permanganate is using. So the important thing to remember about KMnO4 is that there's 2 conditions. Low concentration, low temperature, high concentration, high temperature. And so on the previous exam where solvent matter, with KMnO4, it does matter what conditions you're running at. If you run it under low concentration, low temperature, you end up getting cis diols. So you get OH groups at both sides of the bond and they're on the same side. So if you had cyclohexene, that would be cis when it finished, not trans. If you go to high temperatures, high concentration, it actually ends up cleaving this bond altogether. And you end up getting 2 ketones or aldehydes depending on your double bond. So here's where the mechanism doesn't really matter. Because 1, your theory doesn't adequately describe the mechanism. Lewis theory can't explain why potassium permanganate does this. On top of that, there's 2 different conditions going on here. There is the KMnO4 at high temperatures, high concentrations, and low temperatures, low concentrations. This is going to affect the final product. So really with KMnO4, I would recommend that you not bother with the mechanism and just learn that, you know, if I have high temperature, low concentration, I'm going to get a syn diol. And if I go to high concentration, high temperature, I get cleavage to give aldehydes or ketones. And the question about, well, do you get aldehyde or ketone, that depends on the double bond. So if I redrew this with 2 hydrogens at the bottom, I'd have dimethyl ketone and formaldehyde. All right, Simmons-Smith reaction in a bit more detail. So Simmons-Smith reaction is another one of those. The mechanism is not well described by Lewis theory, and you'll see books attempt to make this discussion. So effectively, what happens with Simmons-Smith is we make what's called a carbene. So a carbene is a carbon with 2 hydrogens and a lone pair, and this actually has a 0 formal charge on it. Like, this is actually a molecule that you can create. And this is why they work with H2CI2, or sometimes you see it written CH2I2. What happens is that this readily decomposes into the CH2, carbene, and iodine gas. There's nothing prohibiting this. Again, this doesn't really, this kind of violates Lewis theory where we say, well, carbon has to have 4 bonds. In this case, it has 2, and it satisfies, definitely doesn't satisfy octet rule, but this molecule does exist. And what your zinc does is it dissociates that double bond. So what will happen is that zinc will accept the double bond, and you'll end up getting this intermediate. And so what happens is that zinc basically bonds with a double bond, and you get kind of like this cyclopropane looking molecule. You've got zinc with a carbon-carbon single bond from the carbon to the zinc. On top of that, you've got this carbene that's also using its lone pair to attach to zinc. And at some point, this will destabilize, and you'll end up getting this 4-square intermediate. You got your CH2 group, which was originally your carbene. You got the first attachment to the double bond, and then eventually this will decompose, and you will break down and get your cyclopropane intermediate. So zinc here is a catalyst, and it serves two purposes. One, it helps decompose this quicker. So what will happen is that in the presence of zinc, it captures and stabilizes this carbene. It also stabilizes the iodine. So you end up creating this really stable carbene. And the second thing it does is it helps break this double bond and facilitate this transition to a cyclopropane intermediate. None of this information is relevant. When you really get down to it, knowing this mechanism is not doing you any good, because there's no way it's predicting anything you didn't already know. Overall, what happens when we have zinc and diiodomethane. So let's say we have some alkene, and we have zinc and CH2 E2. All of that's getting wrapped up in the reaction arrow, and what we're producing at the end of the day is a cyclopropane. This is a really good way to make cyclopropane. But again, knowing this mechanism doesn't really do you any good. Like, it doesn't change the overall outcome. It doesn't help you predict anything. From Francis and Carey, they seem to think that this is a really good thing to know, which is the theory. And if you're a graduate student, I would agree, understanding the theory would be relevant. But this is kind of a debate with teaching organic chemistry. Do I teach you the theory? One, knowing that for zinc, the theory is wrong. That's not what's really going on. It's a lot more complicated. You need to go take inorganic chemistry if you want to know what's really going on. And the second is, okay, I teach you this information, but who cares? At the end of the day, you're making cyclopropane. That's really the only relevant information here. Also the question about hydroboration oxidation. So hydroboration oxidation, I know that's a lengthy mechanism. I'm going to try that one. So hydroboration oxidation, I would also say falls into that same vein of the theory behind why it does what it does is interesting. If you're really into organic chemistry reaction mechanisms, I would recommend you go on to Organic 3. I would recommend you look at a graduate course. At our level, though, one, that theory is kind of not really Lewis theory. If you look at the hydroboration, it's talking about orbital overlap. That is very much molecular orbital theory. What's happening is that you've got borane, which has an empty p orbital, nothing in it, attaching to a double bond. And it will come down, the electrons will fuse, and you get this borane intermediate, and your sodium hydroxide here will attack the less substituted group. And the reason it does this is that it's just easier to get to, so you end up popping that off. So if you've got the more substituted one here, your hydroxide here is going to pop off the boro group, and then you get donation from a hydrogen in the water to get you back to the alkane and get rid of the borane. But knowing this information, first of all, this is not Lewis theory. This is molecular orbital theory that makes this prediction. So Lewis theory can't explain this. We're having to piggyback on molecular orbital theory, which you have not covered yet. And you won't cover until you take inorganic chemistry. The second is that, okay, you know this, but who cares, right? What's more important? Let's say I have an asymmetric alkene. I have a Markovnikov, and I have an anti-Markovnikov pathway. My Markovnikov here is H2O hydroxide, And if I heat it up, I will get a tertiary alcohol. If I use borane, I will get the anti-Markovnikov product. And that's the big picture. When we add to a double bond, we typically add what's called an HX, a nucleophile associated with a hydrogen. Your Markovnikov product puts X on the most substituted carbon. Your anti-Markovnikov puts X on the least substituted carbon. It's a matter of what we want to do. So the Markovnikov reactions are very easy to understand because their mechanisms are very straightforward. X attacks, so the double bond attacks the hydrogen. This creates a carbocation, and then X attacks the carbocation. Is this true? Probably not, but it's a nice, useful approximation for explaining why this happens. The anti-Markovnikov stuff, what makes those things work is typically a lot more complicated because we have to find a way to justify why this big nucleophile wouldn't want to go to what would basically be the most stable carbocation. Excuse me. And so with anti-Markovnikov in particular, you start getting these big complicated mechanisms that are trying to bridge the gap between organic chemistry and inorganic chemistry. I personally do not think it's worth it. I don't think understanding that level of theory, particularly in Organic 1 or even Organic 2, is particularly useful. If your theory is simple enough that it clearly illustrates why it's going on, it's a good theory. But if your theory requires borrowing from another higher level chemistry course, which students have not taken, and in borrowing from it makes a lot of gross over approximations that actually give the wrong idea. So when we start talking about zinc, we start seeing all these bonds coming off of zinc. Not really what zinc does. Bonding of transition metals is a lot more complicated than that. I take that as somebody who did organic chemistry for a whole bunch of years. What you're seeing drawn in the book are gross oversimplifications that are giving you the wrong idea. Do they work? Yes. But they're teaching you the wrong idea in order to make the answer work out. And the one I talked about in the live stream Tuesday that unfortunately didn't come out was my issue with how we teach free radicals. So I used to do... for part of my thesis work, I did free radical removal from fuel cells. And so what happens in a hydrogen fuel cell is you produce a lot of hydrogen peroxide. That can decomposes into free radicals. Those free radicals destroy the fuel cell. So how do we remove free radicals? And the thing is, like, free radical chemistry is really well understood. And if you read the textbook, it completely contradicts all the well understood stuff. So there's two ideas here. So let's say we have our asymmetric alkane, and we're going to add HCl. And what we're going to do is we're going to use light, or H2O2. And this is the overall mechanism. The claim is the first step here is that your light or your peroxide will generate these radicals. I don't have any issue with that statement. That is a true statement. But the claim here is that tertiary radicals are more stable than secondary, which are more stable than primary radicals. I also agree with that. You are more likely to produce, if you can, that radical than you are that radical. A terminal, particularly a primary radical, is very unstable. This is well understood. Here's where it contradicts known theory. The claim here is that the chloride attacks first, because this is the least sterically hindered part of the molecule. Okay, that argument makes sense except for one problem. The rate of reaction for a radical goes as 1 over the square root of the molecular weight. This weighs less than the chloride. So actually what we would expect to see is the hydrogen to attack more frequently. And this is what we see in fuel cells. Hydrogen radicals are the death of fuel cells. They scavenge and they destroy. They catalyze a lot of reactions because they're the smallest element on the periodic table. 1 over the square root of 1 versus 1 over the square root of 35.5. The hydrogen radical is going to attack more quickly. So what you expect to see, based on our knowledge of how free radical chemistry works, is that there's no such thing as an anti-Markovnikov product in this case. Doing this with light and hydrogen peroxide, if anything, should just create weird situations where you have 2 hydrogens or you have 2 chlorines. It should become an uncontrolled reaction. And this is why a lot of people don't like free radical reactions. So why do we claim this? Well, this explanation explains why this happens. Well, the chlorine radical is bigger. It attacks the less sterically hindered, and that's why it attaches to the end. But it completely disregards what we understand about reaction rates when it comes to free radicals. This should react before this one does, particularly because this one's smaller than this one. It should move faster, and it should have an equal chance of attacking both if we really get down to it. But if we're going to say, well, we want to form this more stable radical, this makes a lot more sense to say that this happens first, and then the rate limiting step is this combining with this, but that's Markovnikov. So again, what I'm trying to get at here is that if the mechanisms help you memorize and understand, learn them. I personally, and instructors will disagree with this, I'm sure I will get interesting comments in my chats. I do not think the mechanism, particularly when you get above simple reactions, is particularly useful. I think it's a lot of losing the forest in the trees. And in a lot of cases, the mechanisms themselves contradict what we understand about how these reactions happen in practice. So if memorizing the mechanism helps you memorize it, use it. But if you look at the mechanism and go, I can't learn this, you probably don't need to. Only simple mechanisms, SN1, SN2, E1, E2, and the basic Markovnikov reaction, HX addition to a double bond, those are relevant. And when we talk about alkynes, there are some reactions like the hydrogenation of an alkyne to form a ketone or an aldehyde. Those are pretty straightforward mechanisms that make a ton of sense. They don't contradict anything we know. But once you start getting into anti-Markovnikov, anything involving a transition metal or anything involving a metal, there are mechanisms written out, but there are mechanisms written from Lewis theory, which doesn't really predict what's going on. And so, I know that was a long tirade, but that's kind of the response to that question, is that you don't really need to know the mechanisms, because a lot of these mechanisms inherently are just approximations. They're cute, but some of them contradict known information. So do what works best for you. I generally don't test on mechanisms unless it's a very simple mechanism. So SN1, SN2, E1, E2, and basic HX addition, those you need to know. But as far as like any anti-Markovnikov reaction mechanisms, transition metals, I'm not going to test you on those mechanisms, because especially transition metals, those mechanisms are wrong. They're not correct. And again, I just don't see how they're helping you to know that information. Could be wrong. I've only taught this course for like a year and a half now. Maybe in 10 years I'll change my mind and gone, I really wish I had taught you the mechanisms. But again, at this level, I don't see the merit. So that seems to be it for all the questions I've gotten asked. That was a lot of questions I got asked over 3 days. So if there's any questions, post them in the chat. Oh, no, wait, there's more. Oh, no, wait, that was just a question about how to join it today. So again, I've got chat open if you've got any questions, and it does look like it actually recorded it today, and it does look like we actually have the sound. So again, please feel free to ask questions. I'm just here getting work done. Okay, so a question about epoxidation mechanisms. Again, I'm going to default this to epoxidation. It's probably not one of those mechanisms you need to know. But you are correct. It is a wicked mechanism. So to begin with, we're typically working with a peroxy acid to make this work. And even with the most simple alkenes, if I remember correctly, you go through this 5-membered ring intermediate. Or 6-member. Yeah, it's this weird 6-membered ring intermediate. That decomposes down to something like that. I remember it being some like nasty multi-step intermediate. Download the slides. But I would definitely say the mechanism for alkene epoxidation, not that useful to know. It is an odd mechanism because of how many things have to move to make it happen. And I say this from a reaction kinetic standpoint. Generally, we don't see like multiple bond breaking. We don't see more than 2 or 3 bonds being made or broken at the same time. And this epoxidation mechanism, if I remember correctly, it was some nightmare where like 5 things move at once. There you are. So we got our alkene, and yeah, oh right. So this is how we swap the hydrogen off. And then we get this weird nucleophilic attack. So we end up opening up this carbon-oxygen bond, and this carbon here becomes the OH in the carboxylic acid. This oxygen cleaves this hydrogen-oxygen bond to form initially a bond to that carbon, and then this carbon will back attack to get that oxygen, and in breaking that bond, that bond sweeps down, and we end up forming the ketone. So with the all 4 possibilities, I would recommend draw out all 4 if you can. So it deals alder. So okay, so to finish up on the epoxidation, this is an interesting idea. There are some arguments for the end result of this mechanism to justify, basically use isotopic enrichment to prove where things go. But as far as the reaction itself it goes, even what's in the slide is a gross oversimplification, and it's not very simple. For Diels-Alder, so on test 2, we talked about all the different isomers you can get from, like if I gave you like C4H12, what are all the different isomers? And those quickly became very complicated problems. Diels-Alder is the same way. You can quickly end up with a lot of very complicated answers from very seemingly simple problems. And so particularly with the notes will try their best to stick to simple examples, but I need to reserve some simple examples for exams. So this leaves us with packets that have unnecessarily complicated problems because there are no other simple problems left. We're just going to end up with really hard, complicated answers. So the Punnett square, I've never put in the notes before. I like that idea. I might put that in future slides. But the notes just kind of give you a big picture overview of the Diels-Alder, and that's really as deep as you need to go. But understand that particularly when it comes to like exam questions, which I know is really what a lot of people are really interested in, we're going to stick to simple examples for the exam. So things where it's really obvious, like you only get one product with the Diels-Alder. You don't get this wealth of Diels-Alder products. But unfortunately for things like the packets and the notes, because those simple examples have been reserved for the exam, we're going to end up with notes problems that are actually far more complicated than what's written. But what do you do? But I do like that Punnett square approach. I might add that to a future video. Yeah, the example that's given in the notes is a really simple example. They're all related by rotation. So on slide 57, you technically would have a situation where it's flipped, but if you look at the bottom one, it's just a flip of the top. So you would end up with all those combinations even if you flipped it. And even the reverse synthesis problem, like, it's an oversimplification. So as far as the four solutions go, let's just create our generic there is no generic way to write that. So we're just going to put some things on here to make it a little bit easier to see what's going on. But A, B, C, D can be anything. You can have anything attached to any of the dienes. So your Punnett square here, situation where you have A up and B down, situation where you have B up and A down, situation where C is up and D is down, and a situation where D is up and C is down. In all of these, you're going to have the cyclohexene. But with our cyclohexene, the way we draw the product, this is carbon 1, 2, 3, 4. This is carbon alpha and beta. Alpha is the top carbon, beta is the lower carbon. 1, 2, 3, 4. 1, 2, 3, 4. So for this one, 2 is A, 3 is B. In this case, 2 has a B, 3 has an A. So we flip the A and the B here in what's attached to the double bond. On the upside, alpha is going to have C, D is going to have the beta. On this side, we have D and we have C. So what I flipped here is the C and D relative to the A and B. Down here it's going to be the same thing. So for this one, the carbons on the right, if you're looking down a column, the carbons, what's attached to the carbons on the right flips. So we have D up, C down. Here going up and down, we're changing where A and B are. So here A is up, B is down. Here B is up, A is down. A is up, B is down, B is up, A is down. Going across the rows, we're flipping C and D. So here C is up, D is down, D is down, C is up. Or I'm sorry, D is up, C is down. And same things here. C is up, D is down. As we move to the right, D is up, C is down. But again, if you have something very simple where these are both methyl groups, well, it doesn't matter if you flip A and B because A and B are the same thing. And if C and D are the same thing, the only thing that you're changing is the wedge and dash. That's it. Yeah, you can make C and D cis only if they start out cis. So it deals alder. If these start out trans, they have to finish out trans. If they start out cis, they have to finish out cis. And that's really the only stereochemistry that really shows up with Diels-Alder chemistry. is making sure that whatever is on this far right side, they have the correct cis-trans notation. But they could be cis-trans with one of them up, one of them down. The top one could be wedged, bottom could be dashed, top one could be dashed, bottom one could be wedged. And so what you'll see a lot of instructors do is that they're all hydrogens. And so since they're all hydrogens, we don't have to worry about this. Or they'll do one group, and so cis-trans isn't needed. But yeah, hopefully you see this. Like with Diels-Alder, you can quickly get runaway, really complicated questions, all for making a simple change to the molecule. So yeah, I would love, like, unless all the groups are the same, these problems get inherently super complicated. Which then you just kind of like, it becomes so simple you don't learn anything. Yeah, you're welcome. All right, so just got a question about the bromobutane lab. That's the virtual one. That is a bug in that particular soft chalk module. I'm trying to diagnose what it is, but in order to diagnose it, I have to take it down and then reload it and hope it works. So I'm just working on for future semesters. 85 is the highest score you can get if you've had, like, everyone who's submitting one with an 85 is getting 100. So they're just being gridded out 85 points. But yeah, it is actually a bug with that particular module. All the questions add up to 100, but for some odd reason, it's not counting all the right questions to get you to 100. So again, trying to diagnose, not worth it for this semester. So if you get 85, just submit that. That is the highest score you can get. And quiet at you. That is the highest score you can get, and that just be corrected to 100. All right, so that's it for the live streams today. Again, if you have questions, please feel free to email them in advance. Pretty sure we have one Monday. So have a good weekend, and I will talk to y'all later.